Hi, uh, this is the series of lecture for Solidio Gloria Physical Chemistry, and today's topic is atomic structure. So we are going to talk about spin, of course, because we are going to deal with two and more electron atom. Last week, actually, in the previous lecture, we solved Schrödinger equation of an hydrogen atom. So we have orbital now, so we can combine the idea into multi-electron atom. So we need to talk about spin, and then because of two or more electron, now we have to deal with electron repulsion. That could be handled in two different approximate method. First one is variational principle, and the other one is the perturbation method. So we are going to talk about those two. Let me get the laser pointer. Somewhere I should have laser pointer. Yes. Okay. And then something like for a hydrogen like atom orbital, we say something like 1s orbital or 2s orbital, 2p orbital, like that. So for atom, many electron atom, we have one kind of symbol that designate the state of the atom, that is atomic time symbol. So let's begin. About the spin, 1922, Otto Stern and Walter Gerlach, they did this experiment. They firstly make the atomic silver. Maybe just heating or something. They make a silver atom, evaporate and make a silver atom, and then into the collimating pinhole into the vacuum. So this will make the silver atom beam, and in between magnetic poles. But this is non-uniform, inhomogeneous magnetic field. Notice that this is angular edge and round circular shape. So if those two poles are kind of infinite parallel surface, then we should have a homogeneous magnetic field. But in this case, we have inhomogeneous magnetic field. So if a charged particle or something with magnetic property flighting through this inhomogeneous magnetic field, it should reflect. So let's see. But what they observed is two reflection. One went up, the other one went down. So they marked the position, and which is reflected the same amount to up and down. So that's the result of this silver atom. Let's take a look at its electron configuration. Of course, we now know those things, but it has a krypton core. Yeah, we had this in the general chemistry, so you know this. The krypton core and 5s1 and 4d10. So except the outermost s orbital, all orbitals, inner orbitals, and this d orbital, 4d orbitals are all filled, meaning is they are closed shell. And so we have single electron unpaired. It's just like hydrogen atom. It has just one electron in 1s orbital unpaired. So this is just the same as the hydrogen atom. Just think about that. So this is one electron system. So you are sending one electron system basically through the inhomogeneous magnetic field. Now, for this electron itself has only three coordinates, x, y, and z, and then which is reflected because it has 3 degrees of freedom, reflected into this the symbol, the quantum number symbol. Principal quantum number is 5 for this silver atom. The electron in 5s1, and angular momentum quantum number is 0. And obviously the magnetic momentum quantum number is 0. So this is 500 electron. It has 3 coordinates. So that 5s1 designates a single state, which means that either it's not is one or the other, or just not reflected at all, because considered to be this is just a neutral atom, so it's not charged, but atom itself has something, and that something is magnetic field, magnetic property, but according to this single electron has 3 coordinates, it has just one state. So magnetically it has unique state, just the non-differentiated in this case, but it is differentiated, meaning it tells us that there are 2 states. So there is another coordinate or quantum number is associated with this 47 Ag 5s1 electron. So that electron has another coordinate. Okay, that's one thing. And second thing it tells us is we have only 2 states from so-called the non-reflected zero state. So which means that and also these 2 states need to be represented by a quantum number, either 0, 1, but that does not really fit into this picture, because this reflected from up and down. So the distance from up to down or down to up is just 1. So that it strongly reveals that quantum number must be half integer. So in this case, those 2 are required to explain this experiment. Okay, so firstly, what it was is that there is another coordinate other than x and y and z, or r, theta, phi, which is already reflected in the quantum number, principal quantum number, angular momentum quantum number, and magnetic momentum quantum number. So fourth quantum number is necessary, and that quantum number in this case is half integer. Half integer quantum number is required in this case. So we got the spin. So spin is another set of postulate in quantum mechanics. So so any observable in classical mechanics or in physical phenomena, they correspond to a operator. In this case, spin phenomena requires a spin operator. That's the way we developed this idea. So the operator for spin, angular momentum, is spin angular momentum. Well, by the way, electron is not really spin this way or the other way. Okay, it is just a kind of a state. We have 2 states, and up state and down state in magnetically. So to respond to the magnetic field, so we have the name spin. So there is a spin angular momentum. And that spin angular momentum behave just the same way as regular angular momentum. Meaning is that there are spin operators s square corresponding to L square, s, xn, xy, sg, like Lx, Ly, Lz, like that. And plus minus is a combination of these 2. Actually, plus and minus combine to give you x and y. You remember that we developed 2px, 2py, 2p orbitals from 2p plus 2p minus 1 orbitals. Okay, so that's the way it is done here, the same way. So there are spin operators that does work the same way as the regular angular momentum operator. And also there are only 2 states, and also we need a 2 state, one state called alpha, the other state called beta. So 2 eigenfunctions, 2 simultaneous eigenfunctions to the operator s square and sg particular. So alpha just looks like a spherical harmonic, but in this case we have the L number, L quantum number, in this case S quantum number, or 1/2, and then M quantum number, in this case I would say MS quantum number, in this case positive and negative 1/2. Okay, and then this is the kind of operator relationship to alpha and S. So S square has S plus 1, the same. And for the G component, SG alpha is 1/2 h bar. This one, SG beta minus 1h h bar, 1/2 h bar, okay? So this is the relationship. And also spin coordinate is sigma, we say r theta phi sigma, or xyz sigma, okay? So alpha and beta are a function of sigma, okay? Yes. So I'm not going to talk about, well, and also magnetic momentum. This is a kind of magnetic property as an electron spin. So magnetic momentum of the spin, the magnetic dipole moment of the electron is that mu, just a normal magnetic momentum spin, momentum symbol, mu equals minus G0 beta m as the spin operator. In this case, G0 is that the anomalous spin factor, which is 2.0023, and then beta m is the Bohr magneton. So this is that erg per sec Gauss. Okay, so now regularly we had an orbital. So there is an electron for the even hydrogen. There is an electron which is, let's say, 1s orbital or 2s orbital or 2p orbital, like that, but which is a function of x and y and z, or r and theta and phi. But anyhow, we are going to use the Cartesian coordinate in this case. So psi orbital used to be a spatial orbital, is this psi x, y, and z, or psi r theta phi. Okay. Now we need the spin function. So trick coordinate is for the spatial. So this is a spatial orbital, and alpha of sigma is a spin function. So spatial function times spin function makes the spin orbital. Okay, so this is one spin orbital, and the other one is psi beta. So psi spatial orbital alpha or psi spatial orbital beta are two spin orbitals. So in this case, you notice that this sigma is the spin coordinate or spin variable. And also, notice the spin function themselves are orthogonal and normalized. So alpha alpha d sigma, beta beta d sigma integrated gives give 1, yields 1, normalized, and alpha beta or alpha star beta or alpha beta star equals 0. This is orthogonal condition. So for example, 1s orbital, which has quantum number 100, could have alpha function or beta function. In this case, we indicated half or minus 1/2. Okay, so this is now this is spin orbitals. Okay. So spin orbitals itself, spin functions are orthogonal, and also orbitals are orthogonal. Then spin orbitals are also orthogonal. So the same orbitals gives 1. Same orbitals. Well, this is actually functional integral 0 to infinity, and this has no really kind of like that. But anyhow, alpha alpha equals 1 in this case. Alpha alpha. So 1 times 1 equals 1. So spin orbitals are normalized, and also with different spin, the same spatial orbital equals 0 due to the spin orbital itself. Spin functions is also orthogonal. Okay, alpha beta. Okay. Now, so we had 5 quantum postulate, and I'm going to add one. The 6th quantum postulate is here. Quantum postulate 6. All electronic wave functions must be antisymmetric to the interchange of any two electrons. Well, many electron atom over helium, helium has 2 electrons, and lithium has 3 electrons, like that. So you cannot distinguish electrons in the atom. So if you change or interchange electrons position, or just to change electrons, then, well, actually you cannot change electrons. Anyhow, so you cannot distinguish the electrons in the atom. So any two electrons which is indistinguishable, if they are switched, there is no change in the property of the atom. Then you would require that the probability of electrons must be the same. Okay, does not change. Okay, so indistinguishable particles, if you change their coordinate, interchange their coordinate, or interchange that particles themselves, the probability must not change, must stay the same. And then this condition is that actually psi 12 square, absolute value square, is the probability distribution of the wave function, and psi 21, the coordinate is, or electrons are switched, interchanged, and the absolute value square must be the same. There are two ways to do for this relationship. So first one is psi 21, interchange of 1 and 2, equals to original in plus, with plus sign, or negatives with negative sign with the original of the original. So either way, psi 21 is equal to plus or minus psi 12. This condition is from this. So, and then if this condition is met with plus sign, we call that as symmetric. If this condition is met with negative sign, we call it antisymmetric. So either symmetric or antisymmetric is required for indistinguishable particles. If they change its position or whatever, the particle itself interchange. If those are indistinguishable, this is the condition. So electron is antisymmetric because half integral spin particle, we call those particles fermions. Integral spin particles, we call it boson. Fermions need to meet or represented by antisymmetric wave functions. Bosons by symmetric wave functions. Electron has half integer spin. Half integral spin which is fermion. So for electron, the wave function for electronic wave functions must be antisymmetric to the interchange of any two electrons. Okay, this is the spin postulate, or quantum postulate 6. Now we are ready to deal with helium atom now. So for helium atom, there are two electrons. Well, if this electron is missing here, if we have just one electron, that's hydrogen-like atom with just positive charge 2 in the nucleus. But for helium atom, you have Z equals 2, but you have two electrons. So atom itself is neutral, and then the geometry for this relationship is that, well, actually there are 3 particles. So helium atom has 3 particles, is a 3 particle problem. But Oppenheimer approximation tells us that we can deal with only electrons. Oppenheimer approximation, more or less accurate, precisely, is that if there are 2 sets of different kind of very different degrees of freedom. In this case, we say that nucleus and electrons, their motions, electrons motion and motion of the nucleus are kind of very distinct each other. In that case, we can decouple them and treat separately. So that's Oppenheimer approximation. Maybe your elementary school or kind of early days of your science, it says that, I mean, your beloved teachers told you that nucleus is kind of heavy, much heavier than electrons, so it is fixed while electrons is moving, something like that. So anyhow, if you can understand that way, that's fine, but we can separate their degrees of freedom, and then we treat only electrons motion now here, but with its reduced mass, because center of mass is fixed, and we are going to deal with electronic motion separated from the motion of the proton. So anyhow, so we now include only kinetic energy part, or kinetic energy of electron, not the kinetic energy of nucleus. So first term, minus h bar square over 2m electrons mass, and del 1 square, which is the kinetic energy of the electron 1. Let's say this is 1, this is electron 2. And then minus h bar square over 2m electrons mass, del 2 square. Okay, so this is the kinetic energy part. And then there is electron nucleus attraction energy, electron nucleus attraction energy over R2 and over R1 on this side. So minus 4 pi epsilon, this is the Coulomb part, and then now Z equals 2, so that's why you have 2E and minus C. So minus C times plus 2E is minus 2E square, yeah, 1 over R1 plus 1 over R2. So this is the electron nucleus attraction energy, potential energy, I mean. And then there is this term, which is that E square over 4 pi epsilon naught 1 over R12, the inter-electronic distance. Okay, so if we look at closely about this Hamiltonian kinetic energy plus potential energy, and if I say minus h bar square over 2me del 1 square minus 2e square over 4 pi epsilon naught 1 over R1, this term and that term only, just like this, okay? So kinetic energy and potential energy of electron J is now 1 or 2, which is hydrogen-like atom. In this case, He plus, which is 1 electron. So this is hydrogen-like atom. So hydrogen-like atoms Hamiltonian H of HHJ, yes. So this one and this term makes HH1, this term and that term makes HH2, now interelectronic potential. So we basically have two hydrogen-like atom plus interelectronic interaction. And this hydrogen-like atom is solved in the previous lecture for Schrödinger equation of hydrogen atom. Yes, we solved that. And then we know the energy just given here. As a function of principal quantum number n, j, because we are talking about the electron j, electron 1 or electron 2. So this is the energy of that electron. And then as a function of this R1 or R2, we have the 1s orbital. We are using the lowest energy orbital. So this is the 1s orbital for the hydrogen-like atom with charge G, this one. So if we don't have this interelectronic potential, what we have is that just these two hydrogen-like atom. So the energy itself is that electron 1 energy and the energy of the electron 2. If the energy is the sum, given as the sum, and Hamiltonian is also given as the sum, HH1 plus HH2, then what is the wave function? Which is the product of their eigenfunctions, in this case their orbitals. So electron 1 orbital, electron 2 orbital multiplied make a product, which is the total wave function. Okay, that's it. So if we just calculate with this total wave function orbital product, 1s orbital and 1s orbital, but the coordinate is different, R1 and R2. So first electron 1s orbital, second electron 1s orbital product is the wave function, we can calculate the energy. So this is the energy integral. So energy, if this orbital of phi 0 of R1, R2 is normalized, this will give you the energy. So this will give you the Hamiltonian operate to the wave function, which will yield you something, and then well, this is a form of expectation value of the Hamiltonian that will yield you the expectation value, which is the energy in this case. Okay, so this is it. And then if you compute this carefully, well, you can expand it as a product of psi 1s R1, psi 1s R2. This total operator, actually this one, operate psi 1, psi 2, I will call it psi 1, psi 2, okay? Then this operate only psi 1, that operate only psi 2, then that will give you just this this number, the same number. So that is just about twice of this one, and then what else? Okay, and then, well, actually there is a negative sign, I think. And also we could do integrate 1 over R2 and these functions, and that is done by either numerically or kind of computed in the done way. So that is 27 over 8z as a function of z. So this will give you the idea how much it is. So we are plugging to substitute z equal 2, which is the kind of charge of the nucleus, and now we are getting minus 2.75 h. H is Hartree. That represents this this total. Those are all constant. Yeah, those are constant. So that is the name of this product or division. This constant, which is Hartree. Hartree is a energy unit in atoms and molecules. Anyhow, this is that minus 2.75 Hartree, but actually that is by experiment. That energy is accurately measured. An accurate value is negative 2.9037 Hartree. So there is that much discrepancy. Maybe it's not that big, but that's really big because Hartree is a very big number. So if you ignore this interelectronic potential and make the total wave function as the orbital product, you are ending up with this. You ends up with this discrepancy in energy. So you need to do better than this, or that's why you have to deal with this interelectronic potential. So first way is variational principle or variational method. Second way we are going to talk is the perturbation method. Before we do that, let's define some atomic unit. Okay, this is kind of a little bit complicated, and there are many constant terms appears here. So we define mass unit by electron mass, charge unit by electron charge, angular momentum h bar, there is a bar, it's not really visible, well visible, and distance a0, which is Bohr radius, is given here, and energy, just we talked about the Hartree. So that is that kind of real in value. Permittivity also 4 pi epsilon naught. All these quantities is unit. So for the place of this me, just like here, we just put 1. For the place of h bar, we just put 1 because this is the atomic unit. So in atomic unit, this complicated Hamiltonian for helium atom is reduced to this one. So there is no complication with constant here, but whatever value you obtain, if there was energy, the unit is atomic energy unit, which is Hartree. And if you calculate some like distance, that is in Bohr radius. So just to keep that in mind, your Hamiltonian is in very simple form. Okay, I told you that Hartree is kind of big number. It's very big energy. So this is the all constant. You put electron mass in kilogram, electron charge in coulomb, and this is just numbers with pi. Actually, 4 pi epsilon naught, the permittivity is here, and permittivity square, and then h bar is here, and then that's h bar square too. So all this ends up with the unit joule, and that's the joule in kilojoule per mole, which is 2625.5 kilojoule per mole. So it's about 2600 kilojoule per mole, which is big energy. And then this is the equivalent to, in kilocalorie per mole, 627.456 kilocalorie per mole. These two numbers have in mind, just to know, put it into your brain. Okay, so these numbers you know, and then you may calculate the wave number of Hartree equivalent, which is this 2.1947 to the times 10 to the 5 reciprocal centimeter, which is the wave number, and Hartree is that wave number. And also Hartree in electron volt is 27.211. Actually, I think that I recommend to remember this one and these two. Okay, so 3 numbers you need to know about Hartree. Okay, so first approximate method is the variational method. Well, I say approximate, meaning is that you are getting precise number. Yeah, just the same as the experimental precision. You will get the precise number, accurate number. Method itself is approximate because it does not yield you analytical solution. That's the meaning of this approximation. So you don't get orbital in functional form. Other than that, you as far as number-wise concerned, the quantity is concerned, you are getting accurate number, or at least we try to get the accurate number. That's what it is. So instead, the analytical form of wave function, you are getting some kind of series solution or combination, linear combination of some basis functions. That's what you get. So, but still, the energy and other quantities you are getting is very accurate, or as accurate as you can. Okay, so variational method or variational principle tells you the ground state. Well, basically you are always getting the lowest energy possible. So the ground state is the lowest energy state. Ground state wave function psi0, and its energy is E0, or psi naught and E naught. And this is the relationship, H psi naught equals E naught psi naught. And the energy itself is given here as the energy integral. And then if this psi0, psi naught is not normalized, then you have to divide the Hamiltonian integral by its overlap integral. So anyhow, this is the relationship coming from, well, just from here. You just put psi naught star from left hand side and integrate it, and then E naught is the constant, So you're ending up with this integral equals E naught and this integral. So E naught is this divided by this. Okay, so this is the energy integral. And the variational method tells you that any trial function which mimics psi naught or whatever, just guess, or just say educated guess, something like that. Any trial function psi for psi naught with has the energy just like this, is in the position of psi naught, you put just a phi. But this energy for phi is always greater than or equal to E naught. That's the variational method. So this will guarantee you just to do your best. In a way, just try to get close to psi naught, making your trial function, make your trial function phi as close as possible to psi naught. Still, your energy is going to be greater or equal to E naught. So just to vary this trial function and lowest possible energy. Okay, you just go to the lowest possible energy with this phi, then which is still greater than E naught, and you are safe. So you just try your best to get phi, the E phi, lower E phi, lowest possible E phi with your varying your. That's why the name is the variation, varying your trial function phi. Okay, so there is a proof. You can prove this. So this is the regular Schrödinger equation for energy, the psi n for eigenfunction of this Schrödinger equation is psi n with energy En. So you can expand your trial function in the basis of psi n, which is sigma n Cn psi n. So as a linear combination of psi n, you get phi. So this is your trial function. This is completely general. As per se, if this is this psi n expand entire space, then this is kind of accurate statement. But if that's not the case in general, so you are limited in number, n is kind of finite number. So this is not really that accurate, but anyhow, this is the kind of one way to express this phi in general. And then E phi is here. So E phi is given. You may just work out by your with the pencil and pen. I mean pen and a paper. You can work out this, and then E phi minus E naught is given here. E phi minus E naught. So basically, this is E phi, this is E naught. Okay, E naught, but E naught itself is E naught times this and time divided by this. But this is just also normal condition. So normalization condition. So also that is also normalization condition. And then you can combine numerators in this way. And then the smallest number is of En is E0. Okay, so En always greater than or equal to E0. Meaning is that this entire thing is always greater than or equal to E0. So E phi minus E naught is greater than or equal to 0. Okay, I don't know why. En is always greater than or equal to E naught. That's because of this, and we can guarantee that E phi is always greater than or equal to E naught. That's the proof of this. So variational method is that you obtain your variational integral the variation energy as a function of all these parameters, alpha, beta, gamma parameters. Those are variational parameters you can vary in order to lower the energy. So just get the lowest possible energy in terms of alpha, beta, and gamma, which is obtained. First derivative against alpha, beta, and gamma are all zeros. So when these condition is met, you have the lowest of E phi, which is greater than E naught. So this will give you the best phi for psi naught. Okay, so this is how you obtain to solve the Schrödinger equation. Approximate, but the best. So for helium atom, now we are back to the problem of helium atom. So firstly, we do variational method. So this is the Hamiltonian. You remember that in atomic unit, and our trial function is just the same as before. So orbital product. So electron 1 in 1s orbital, electron 2 is also 1s orbital. Those are lowest possible energy orbital for one electron. Okay, so this is the 1s orbital in functional form in R. This is a radial part only because the s orbital does not have angular dependency, so we don't have angular part here. And now Z is atomic number used to be, but G is the variational parameter. Okay, so well, actually, due to screening, not in this case, but due to screening, or well, in this case too, screening by another electron, so that atomic charge could be reduced. Okay, so we obtained this before by using this orbital product wave function, which was g squared minus 27 over 8z. And then if you make a derivative this energy with respect to z in this case, then you get 2z equals 2z minus 27 over 8 equals 0. Yeah, then your z is half of this number, so 27 over 16. Yes, yeah. And then using this number, you obtain this energy is this. So your variational approach with the nuclear charge as a parameter, variational parameter, is this. So what you have is negative 2.8477. You remember that we are using atomic unit. So this number, this energy is in Hartree. Yes, this is Hartree. And also, if you obtain the energy and experimental value, energy is always relative quantity. You remember from thermodynamics that energy is a state function, but you don't know the absolute zero because you can always obtain the difference from state to another state. Yes, so this is the difference from one state to another. So in this case, the reference state is I would say atomic state and ionized state. Okay, so, and this ionized state, helium goes to helium plus ion. This ionized state is hydrogen-like atom, which means that we can obtain energy accurately or just precisely or analytically. Yeah, so that is just this number. Z is now 2 instead, 1 for hydrogen, and this quantum number n equals 1. Okay, G equals 2 and 1 equals 1. What we get is just 2, minus 2, negative 2. So this hydrogen, helium plus ion energy is minus 2. Okay, this is minus 2. Okay, then we obtain this number. Then what we have is that minus 2 minus the energy E min is the ionization potential. So minus 2 minus this is 0.8477 is the ionization potential. Then in Hartree, which is 22 26 kilojoule per mole, which is big number, but this is what you obtain. But there are experimental number known for helium ionization, which is in Hartree minus 2.9033. So yeah, that is well, I'm sorry. Ionization potential is known in kilojoule per mole. So in terms of Hartree, and we obtain the experimental energy, which is 2.9044. What do we obtain? Minus 2.8477, something like that, if I recall it from the previous slide. Okay, so there is another there is an approach to obtain this. This is the experimental value done by Slater, and actually he devised a orbital, Slater orbital, 1930, and which is as a function of r theta phi, just as a regular function, and that has normalization factor and spherical harmonic, but only r to the n-1's power and exponential. This used to be what? Laguerre polynomial. But Slater's idea is just a single term, like single term in the Laguerre polynomial, and also he can combine as many as he likes. So he could do actually mimic or represent an orbital. So this is we call Slater orbital. Okay, so this is the normalization, and then z, exponential exponential factor here. Z is the variational parameter. It's not necessarily the capital Z of n. That is actually we call zeta. Zeta is the in Greek. Zeta is the variational parameter. So the orbital product itself is now S11 NLM. Which is 1s, S11, R1 theta 1 phi 1, R2 theta 2 phi 2, but with the variational parameter zeta cube over pi and exponential to negative 2 zeta R1 plus R2. And you compute the energy, variational energy, and make a derivative against zeta. What you obtain equals, then make it 0, equals to 0. What you obtain is 27 over 16, just the same as before. And then, yeah, we haven't done nothing yet. And then, okay, then what you obtain is minus 2.8477, and then ionization energy is 2226, and that's far from here. Experimental value maybe 111 kilojoule per mole difference in ionization energy, error in this case. So you can obtain or improve this trial function by including more variational parameter. Obviously he tried now this n was 1 in this case, in the previous case. So now put n equals n, treat n as a variational parameter. So your psi has to, because psi has n here as a parameter now. So the make obtain the energy, variational energy, and make a derivative against n and zeta. What you get is these two numbers. And with these two numbers, you notice that this is not really the same as before. And then your energy is in Hartree minus 2.8542. Then if you subtract this from minus 2, obtain 0.8542 Hartree, which is in kilojoule per mole 2242. So actual number is 2373, 2226, 2242. That is improved by something like 16 kilojoule per mole, right? Yeah, little improvement by just releasing one or including one more parameter. And if you do more flexible function of this product orbitals, and you would get much better, not much better, better result. So it says completely general phi r is the best value. Of course, it's completely general, and which is obtained, and the energy is obtained -28617, and then ionization potential is 2262 kilojoule per mole. So look at this: 2226, 2242, 2262, 27, and 2373. So kind of improvement done by including or making the trial function more or completely flexible or general. Okay, and this is the limit by doing this product wave function. Orbital product wave function is the limit, and that limit we call Hartree-Fock limit. Yeah, remember this term. This is very important. Hartree-Fock limit. Yeah, Hartree-Fock equation or Hartree-Fock way of doing energy calculation and wave function calculation. Yeah, we calculate the wave function. How? Because wave function itself is a expansion of the basis function, and then we determine the coefficient for the expansion. Then that is the way we calculate the wave function for the state. So firstly, we'll make this kind of general idea later on, but firstly, for helium atom there are only 2 electrons, so trial function is the orbital product. So orbital product way is Hartree-Fock method. Okay, that is the we call it. So orbital product is phi of R1, phi of R2, and then let's say, for example, we know this function phi of R2. We know this function. Then we can compute the potential energy of 1 due to the electron 2. Okay, so which is done here. V1, the potential energy of electron 1 effective due to R2 is, you just integrate in with the known function. Integral phi star R2 known, 1 over 1 R12 phi R2 known, function dr2, of course. And once you know this, and U effective Hamiltonian for R1, electron 1, is the kinetic energy part and potential energy part, hydrogen-like atom, and this effective potential. And then you can determine the wave function phi R1. So basically what you have done is you know this, and then you calculate the effective electronic potential, and then you assemble this effective Hamiltonian for electron 1 and solve it and obtain epsilon 1, the orbital energy, and then phi 1. And then you compare that. Of course, at the very first step, you don't have anything to compare. You have to go up. Now you have phi 1, and then you determine phi 2. Yeah, and then you can compare phi 1 phi 2 from the previous given one with what is obtained here. And if they are the same, you've done. But that's not usually the case. You have to reiterate this procedure until you obtain this consistency from the previous step. So this is the kind of what we say self-consistent field. So this is self-consistent field or SCF calculation. So when this self-consistency is kind of meet, then you've done. So you obtain the energy and your wave function as the orbital product. So Hartree-Fock limit is, firstly, they did 5 Slater orbital. You see that there is a zeta 5 function and the combination coefficient, 5 of them. So 5 is kind of flexible enough, or more or less kind of limit. If you increase one more term, 6, maybe 7, does not improve much. So this is kind of limit, and you reach the this is completely general, so you have reached Hartree-Fock limit. And he obtained Hartree-Fock energy minus 2.8617, which was, we have seen this, 2262 kilojoule per mole. So this is the energy, the best energy you can do with this orbital product. And then there is a correct energy from the experimental value of ionization potential, and which is minus 2.9037. Well, this is the kind of a bit different, but this is the, this is not experimental, but more accurate in calculation. Yeah, experimental also has an experimental error. It entails the experimental error. So this is known to be the exact number. And the exact number, exact energy, difference from the exact energy and then Hartree-Fock energy, orbital product energy, is what we call the correlation energy, which is, as I said, 110 kilojoule per mole. So correlation energy also, this Hartree-Fock limit and correlation energy, be familiar with them. Okay, there is another approach. We have talked about variational method. Now there is another approach I'm going to talk about, which is perturbation treatment. So kind of imagine that you want to calculate, you want to obtain the area of this shape, which is very similar to rectangle like this. And then what you can do is that the area of this rectangle and subtract or add negative of this small rectangle over here. Okay, so that's what you're doing. So there is a problem with Hamiltonian like this, and then there is a very similar to that, but which is exactly solvable. This is easy, just width times I don't know what you call it, but side. Yeah. Okay, which we call H naught. And then little thing is the perturbation. So in the helium atom case, there are two hydrogen-like atoms. So these two together, kinetic and potential. This is exactly solvable. We call it HH1 and HH2. And this is this. This is exactly solvable H naught. And this part, the electronic potential energy term, which is perturbation in this case. So this is how we break up the problem: exactly solvable and perturbation. Exactly solvable up to here and perturbation. Likewise for the general oscillator, not harmonic oscillator, enharmonic oscillator. Kinetic energy term and harmonic term, and then enharmonic term here. So up to harmonic term, we can solve it exactly because we have done it with Hamilton differential equation for harmonic oscillator, of course. So harmonic oscillator term is that we call exactly solvable, and then these two enharmonic terms can be treated as perturbation. So this is the approach we do now. And then the kind of theoretical development is just like this. And well, it is getting really complicated beyond first order. So we just derive the first order perturbation theory here. So this is the original problem, and that Hamiltonian is break into exactly solvable and the perturbation. Okay, and then exactly solvable is just H naught psi naught equals E naught psi naught. Okay, and then psi itself is psi naught plus delta psi, which is corresponding to or explaining to H1. Okay, so H1 is the perturbation, and delta psi and delta E are small. And also what I mean by delta E is that energy is a little bit different from this exactly solvable energy plus, so it's plus delta E. So we are going to determine delta psi and delta E. So probably we are going to just do delta E only here, but we could do delta psi, and then we are going to go further in second order, third order, like that. So first we try to obtain this one. That's very simple here. So using this and this and that in this equation, this equation with this Hamiltonian, this wave function, this energy is expanded here. So firstly, H is H naught plus H1 applied to psi naught. So H naught psi naught, H1 psi naught, and H1 applied to delta psi. Okay, here. And energy wise, energy side, this side using this side using this and wave function. Okay, so this is E naught psi naught, E naught delta psi, delta E psi naught, delta E psi delta psi. And this delta small times small, smaller, much smaller. So we disregard. Let me use pen now to note this. Disregard this, and this also small times small, disregard that. And then we have 3 terms both sides, but H naught psi naught equals E naught psi naught. You see, that's exactly solvable. So this also exactly solvable. So that also it's kind of difficult to manipulate. Yeah. Okay. And this also canceled each other. And so 2 terms left here and another 2 terms left there. Okay. So what we have here is just these 2. And what we can do is we are going to get delta E. And what we do is that multiply from left hand side with psi naught star, just like this. Let me just do it. Psi naught star. Let me get the pointer. Yeah, psi naught star, and everywhere psi naught star, psi naught star, psi naught star, psi naught star, and then integrate. So, but before we do that, we can combine this and this. So this transfer this term to the left hand side and put minus sign here, and then put them together. Okay, and then just to this term, then equals E naught. This move there, delta E, and this integral. This integral is 1 if psi naught is normalized. Otherwise, we just divide both sides with this. And then this is 0 because H naught itself is a Hermitian. So Hermitian property is this equation. Okay, so this equation is here, and then you switch this and that and put star here, and energy is a number. If you put star, it doesn't matter, it doesn't change it. So basically what you do is that this goes to this side, and delta psi goes to the other side, this side, but we separate it in this case this way. And then H naught operate to psi naught, which is E naught, and then E naught is there. So E naught minus E naught is the result of this H naught psi naught operation, and that's equals 0, and that's equals 0. Meaning is that you don't need this one. And then what you have is that if this is normalized, delta E is equal to this integral. So delta E equal that integral is here. And the meaning of this integral equation, that's not an integral equation. This equation is that delta E, the energy correction, the first order perturbation energy, or the first order, according to the first order perturbation theory, the energy correction is that expectation value of the perturbation in the exactly solvable or exactly solved wave function, meaning is here psi naught. So integral psi naught star expectation, this is perturbation H H1 psi naught d tau, which is the expectation value of H naught in psi naught. I'm sorry, expectation value of perturbation. Yeah, H1 in psi naught. Yeah, delta E. So energy is now E naught plus the correction delta E, and maybe this is the first order term, and maybe higher order term. Then you can get accurate result. So now we apply helium atom, the perturbation treatment to helium atom. Yeah, I'm sorry, this is a little bit getting longer. Well, actually what I did is that it took 2 hours. So I recorded 2-hour lecture this morning, and the audio didn't go through. So I obtained the no audio 2-hour video. So I'm doing this now. It's already maybe close to midnight, but I'm doing kind of several times this one. Okay, bear with me, and maybe 1 more hours, not that much, because I'm doing many times now, so it's getting faster. Okay, so let's apply this perturbation method to the helium atom. Okay, so for helium atom, remember that this is the exactly solvable H0, and this is the perturbation. Okay, so this is H1, HH1, HH2, H0, and psi is the orbital product of course. Then this is the exactly solved problem. And then E0 is just the twice of this, the same. N1 is N1 and N2 equals 1, G equals 2. So that's what you get obtained previously, and this is your perturbation. Then what you are going to do is that get the expectation value of this in this wave function. Okay, expectation value of that in this wave functions. And because you don't have star here, because these are real functions, and that's what you obtained in this integral calculation. Okay, so this plus this is your energy, and then all this what is in parentheses is equal 1, because all are in atomic unit. Okay, so this is it, and then what you obtain is minus g squared over 5 over 8z. Okay, so g, if that capital G is 2, then this is what you get, minus 2.750. Actually, you did not do anything in the first order. Okay, you remember that this is when we kind of the very beginning, at the very beginning, we just disregard, ignore this, and then get get the wave function as the orbital product, and then integrate to this, and then we obtain this. Yeah, just the same as before. So this is what you obtain in the first order perturbation theory. And variational result, which was at the same level, same flexibility, just with this, was minus 2.8477, and this is much frustrating compared to this. When you just treat this capital G as a variational parameter, you could improve this much, but as a first order perturbation treatment, you obtain just this one. But you've done just a first order treatment, and then you may do second, third, fifth, maybe hundreds, thousands treatment. Then you would get this number quite easily. Actually, you got in 13th order perturbation theory will yield you this number. So this is the kind of summary of variational and perturbation treatment. Actually, the comparison of how it works, how those working. Experimental value for the energy is minus 2.9033. Actually, yes, and this is the ionization energy, 2373 kilojoule per mole. This is in Hartree. So we are going to calculate how much ionization energy is different from experimental value. Okay, so zeroth order calculation, meaning is you don't include the perturbation at all. No interelectronic term, which is -4, and this is kind of terrible. But first order improved this much already. Okay, so the difference is from here is that 404, and second order -10, impressive, and 13th order eventually will give you 0, and that is the much accurate value than experimental energy. That's why we had so-called exact energy minus 2.9037 while we are talking about correlation energy. I use this number. And in terms of variational calculation, and only one variational parameter, you obtain this number. Okay, so which is 147, not much impressive, but adding one more n as a variational parameter, then you get this. And then Hartree-Fock limit 5 function, which means that you had 10 variational parameter problem, then that is 111. And this is the Hartree-Fock limit in variational calculation. And Hillera did include 1 over R12 internuclear distance as a kind of this is not orbital product itself, but it's a kind of different function. But that function is a function of R12, the interelectronic distance. And 10 parameter Hillera approach in variational method reduce this pretty much impressive, just 1 kilojoule per mole difference from experimental value. And Percury did 1078 parameter calculation. He obtained exactly the number, experimental number, and the experimental energy. More accurate the energy than experiment. So this is way we've done. Perturbation treatment is rather complicated than in terms of computer coding, which is much easier. Variational method is much easier. It's much flexible, and so we rather sacrifice some accuracy, but we try to do first to achieve the Hartree-Fock limit in variational calculation. In usually the computational chemistry concentrate utilize this method, and then go beyond recover Hartree-Fock limit to recover the correlation energy. That is usually what we say quantum calculation. That's the usual way in quantum calculation. So now we covered the approx method, and basically we know how to deal with the 2-electron system, and then expand that we can do multi-electron system. But what we have done is that orbital product be the wave function of 2-electron system. So this is one of them. So psi12 is either 1s alpha 1, 1s beta 2. Okay. Well, basically 1s alpha is the spin orbital, 1s beta is also spin orbital. What if you exchange the electrons, electron 1, electron 2. So 1, 2 is now 2, 1. Now 1s alpha 2, 1s beta 1. So if you compare psi12 and psi21, they are not symmetric nor antisymmetric. If you switch, if symmetric means that psi12 equals psi21, antisymmetric means psi12 equals to minus psi21, something like that. Yeah? So it's not symmetric nor antisymmetric. So if you want to symmetrize, this is the way. You just psi12 plus psi21, which is psi1. Yeah, first way I would say. And what you are doing here is 1s alpha 1, 1s beta 2 plus 1s alpha 2, 1s beta 1. If you interchange 1 and 2, you would get the same, which means that psi21 is equal to psi12. So that is symmetrized. If you want to anti-symmetrize it, what you do is that psi12 minus psi21. In that case, 1s alpha 1, 1s beta 2, minus 1s alpha 2, 1s beta 1. If you interchange 1 and 2, meaning is that psi21, okay, then which is psi21 minus psi12, okay, and then that is minus psi2, psi12. So psi21 is psi12, which is antisymmetric. So antisymmetric and normalized is this function. This function requires normalization factor 1 over square root of 2. So this is the right. This is not right because they are not antisymmetric. This is right. This is right. Antisymmetrized wave function for helium atom. Yeah, it's complicated, but we are lucky. If you take a look at this carefully, more closely, and this could be represented in this way. So 1 over square root 2, 1s alpha, 1s beta, 1s alpha, 1s beta, 1 and 2, and minus 1s beta 1 minus times 1s alpha 2. So this could be represented in matrix form. I'm sorry, determinant form. So this we call a determinantal wave function, the same as this one. We just put it different way. And this determinant is the Slater determinant. So this is Slater determinant, mean that that's multi-electron wave function, anti-symmetrized. So if you have an electron, not two and more, an electron, what you have is that the total wave function is in Slater. It's easy to write in Slater determinant 1 over square root of n factorial, which is normalization constant, and you could well use this small u. One is the first orbital, u2 second, and un nth orbital. Okay, and then you write your first electron, second electron, and nth electron. So orbital index is this way. Electron index goes this way. Okay, yeah. So basically, if you remember recall that our power principle, you just put electron over electron over electron like that. So electron index this way and orbital index go that way. Okay, either way, mnemonic device. So, and this is rather kind of difficult form to write down or in your typing. So what people usually make a notation, the Slater determinant, in such a way that don't usually put this one, but only put this trace diagonal element in this between this vertical bar. Okay, so vertical bar and u11, u22, unn. Okay, this if you just single line, if you look at this one, you automatically or just directly see this one. Okay, so this is the way we represent the Slater determinant. Right. So this is the generalization for Hartree-Fock self-consistent field calculation. Formally, it is done by Hartree first in 1928. Hartree made the multi-electron wave function as the orbital product. So we call it, honoring him, Hartree product. Okay, and each orbital is radial part and angular part, just a normal. It could be a Slater determinant or any expansion over basis functions, an orbital. And then we just to do the same way as same calculation as helium. Firstly, we compute that the interelectronic potential due to interelectronic potential of electron I due to all other electrons except I, of course. Yeah. So that is the electronic energy of, in this case, what you are calculating here is because we're using UJ, and then this is the interelectronic energy of I and J. So this is the interelectronic energy of J, of electron I, in the field of, or due to electron J. Yeah, you understand that? Okay. Then you collect all this JJ except I. Then that's interelectronic potential of electron I in the field of rest of the electrons. And then this is kinetic energy of itself and potential energy of itself to the nucleus. So that's effect. And all variables here is that ice electrons coordinate. And then you could solve this, just one single electron problem now. And then you obtain UI. So you obtain UI, then you could do another one. So you are starting with your guess or some kind of trial series orbitals, and then you obtain JJ, and then you assemble effective Hamiltonian and solve this single electron problem, and then accumulate that result and then compare it from the previous step. And if that's same, you stop, you obtain the orbital energies and wave function. But if not the same, then you go back and repeat or iterate this self-consistent field calculation until you obtain self-consistency. Then that's the answer. So, but obvious problem here is that this is not symmetrized, anti-symmetrized, of course. So 2 years later, Fock introduced anti-symmetrization to the Hartree product, meaning is that he used the Slater determinant. That's the way. That's the year Slater proposed that Slater determinant, I think. So this one electron effective Hamiltonian, we call it Fock operator. So Fi Ui equals epsilon I Ui. So this is the orbital energy, and then this is the Fock operator Fi, and then Ui is the orbital. So this is in general, this is the general way we carry out Hartree-Fock calculation. Okay, we are almost close. Yeah, we are close. We are getting close. And then at this point, we are dealing with many electron atoms. At the beginning, I told you that we need a device to designate the state of the atom. It was easy, or it is straightforward for hydrogen atom, because hydrogen has only one electron. So we could say 1s or 2px or something like that. Then that is the state of the electron of the atom, meaning is the state of the atom. So in this case, we have more than 2 electrons, and we want to have a symbol designate the state of that atom, or designate the state of the electrons of the atom. That's kind of electronic state. Yeah, electronic state of the atom. There is a symbol for electronic state of the atom, that is atomic term symbol. So before we jump into that topic, let's talk about how we obtain the symbol for the electron in hydrogen-like orbital, hydrogen-like atom. So in that case, if I say it is 1pg or 1p0 plus something like that, how do I know it? Because there are quantum numbers. N equals 1, L equals I'm sorry, n equals 1, yeah, n equals 1, L equals p orbital 1, yeah, m equals 0, plus is from spin quantum number plus 1/2. So those 4 quantum numbers, a set of those quantum number gives me the idea what is the state of it, of the electron, or the hydrogen atom. So in this case, there are many electrons. So before I jump into that argument, so that 4 N, L, M, MS, these 4 quantum numbers are obtained from the corresponding operator, which is total energy operator, Hamiltonian, and angular momentum operator, and spin momentum operator. Okay? From those, well, actually, ML is from component of the angular momentum operator. Anyhow, this in this case, the operator itself H, L square, LG, and S square operators. These operators is a first H operator, Hamiltonian operator, gives us idea about the energy state. So which is 2. I'm now still talking about 2p0 plus. Okay, and then L square operator gives us the idea, which is the L number is 2. Then I have 2p, and finally G means that ML quantum number, so-called LG operator, gives us that the state is 0, and then S square operator gives us that I'm sorry, yeah, 1/2, but plus means that SG operator gives us idea that S plus 1/2. So in this case, these operators set up the state, or the symbol for the state, 2p0 plus. Okay, just like that. So for because these angular momentum operators, spin angular momentum operators are commuting or independently designate the state with Hamiltonian total energy operator. So total orbital angular momentum L and total spin angular momentum S of an atom are conserved. Meaning is that conservation of motion, meaning is that they are commuting with the total energy operator H. So Hamiltonian mean. So those will give us a good quantum number in a way that they are not kind of mixing each other. So there is no cross term. So kind of making its scope very separately. So that's kind of the idea here. So what we are going to do, or we are going to apply here, is that we will find a good quantum number for multi-electron system, which should commute with the Hamiltonian. The candidate for that is angular momentum and spin angular momentum, because they are constant of motion, and if the operators are representing the conserved quantity, then they should commute with the Hamiltonian operator. That's the idea. So L operator is the sum of small l's, and of course LZ is the sum of LZ's, and then ML is running from minus L to L and or integers in between. So for electrons, what we have is that L1 plus L2, and then this L value, and up to absolute value L1 minus L2, okay, and in between. And S operator is sum of Si, and SG is sum of SGIs, of course. Then MS is running from minus S to plus S, and in between numbers. Okay, for 2 electrons is either S1 and S2 are both 1/2, so equals to 1. S1 minus S2 equals 0, so only two numbers like 1 and 0. And then you can also combine these angular momentums, like the just general angular momentum, J equals L plus S. And then L plus S runs from L plus S plus minus 1 up to L minus S absolute value. And Mj is done with minus J to J and integers in between. And we have in mind in this the eigenvalue equation, eigenvalue formula, L square eigenvalue is L plus 1 h bar square, S square eigenvalue is SS plus 1 h bar square, Lg is ML, Sg is MS h bar. Okay, so these things have these things in mind, and actually this is a vector model for angular momentum based on the vector model of the angular momentum. So now we are at the position to do atomic term symbol. And as I said, electronic state of an atom are designated by this commuting angular momentum operators that yields the good quantum number. So we get the good quantum number and then notate that quantum number, set of quantum numbers. So this is done in this way. So L value is in the kind of key. So L is the total angular momentum, the orbital angular momentum quantum number. So L value equals 0, 1, 2, 3, 4, 5. In this case, we use SPDF, just the same as orbital angular momentum. Yeah, it's the same, but this is total orbital angular momentum. But for single atom, we do the same, but in what? Lowercase. We are using uppercase, capital SPDFGH. That represents the L quantum number. And then left superscript is 2s plus 1. We call this the spin multiplicity. So obtain S number, 2 times it, 2s plus 1 is the spin multiplicity, which is left superscript. And right subscript is the total angular momentum quantum number J, which is L plus S minus 1 up to L minus S absolute value. Okay, this is how you obtain atomic term symbol. And then one idea behind it is the Russell-Saunders coupling. In other words for that, we sometimes call it spin-orbit coupling. And in order to use this J, and we obtain that J value from L plus S minus 1, L plus S minus 2 up to L minus S absolute value. What we assume that is there is no or negligible coupling between orbital angular momentum and spin angular momentum. In that case, J is the good quantum number. The condition for that is the atomic number is less than 40. In that case, that's kind of safe to use. And then that is the condition for the spin and orbit coupling is far less than electron repulsion. Yeah, that's the idea. So in that case, L and S are kind of good quantum number in a way that we can treat them separately. So people say that in modest mind, almost good quantum numbers. So Russell-Saunders coupling is just to do J equals L plus S in the vector model. So basically that's the idea when we obtain J value, how we obtain J value. So atomic term symbol for helium atom, which is 1s2 system. And it's not really important here because inner shells are all filled, we assume, in the ground state at least. So in this case for helium, Ml equal 1, Ms equal half, and then Ml2 equal 0, ml1 equals 0, ms1 equal plus half, ml2 equals 0, ms2 equals minus half. Okay, this is the kind of our configuration of 1s2. Then ml value is L1 plus L2. Well, actually, L1, L itself is 0. So 0 and ms is this plus that equals 0. Okay. So L equals 0, S equals 0, J equals 0. Yeah, 0 plus 0. Yeah. So this is L equals 0 is S equals 0, 2 times 0 equals 0, plus 1 is 1, singlet. So 1s, and 0 plus 0 equals 0, which is 0. So the term symbol for helium ground state is 1s0. Yeah, I don't know. I think that people say 1s0. I'm not really that native in this field, but 1s0 is the way I say. Okay, there are two things we need to know further before we go further. All field shells or closed shells, S2, P2, D10, F14 are 1s0. Yeah, this is 1s2, S2, so 1s0. This all field or closed shells have 0 spin and 0 angular momentum, orbital angular momentum. So L equals 0, SG equals 0, then SJ equals 0, then this is the term symbol. So all field shells, closed shells, we don't consider because that's 1s0. If no other electron except those shells, then that's the state, term symbol. And also, when we consider P5, 5 electrons, we have to consider that, but which is exactly the same as P1 system. So the state of the hole is the state of the electron. So Pn state are identical to P6 minus n state, and Dn state are identical to D10 minus n state. So maybe Fn system is equal. The Fn system is the Fn systems are identical to F14 minus n state. Okay, so that's the idea. Because there are many micro states. For example, if there are n electrons and G equivalent spin orbitals, this many micro state, G factorial over n factorial, G minus n factorial. For example, P2. So P has 6 equivalent spin orbital. That's right. Px, Py, Pg, and each spatial orbital you have 2 spin, so 6 orbitals. And 6 factorial, divide by it. If there are 2 electrons, 2 factorial, 6 minus 2 factorial, 4 factorial, then what you're ending up with 15. Yeah, so 15 microstate for P2. So we are going to look at this closely. So this is P2 system. And then we just list all possible microstate here. And MS case is either these 2 electrons is either plus half and or minus half. So plus this plus superscript meaning plus half minus half, like that. So plus half gives 1, minus half plus half 0, minus half minus 1. Okay, and ml value. L value is that usually if that's P system, you can have L value equal 1, you can have 0, 1 or 0. So both 1, 2, or one of them is 1 and the other one is 0, 1. Both 0, 0, or 1 minus 1, 0, just like that. 1 minus 1, minus 1, minus 1, minus 1, minus 2. This ml value. And now, Pauli exclusion, requires that any 2 electrons can have the same set of quantum numbers, meaning is that both electrons can have 1, 1, plus the same. It cannot be the same. Both either, you could do 1 plus, 1 minus, that's okay, but 1 plus, 1 plus is not possible or allowed. So you cross out like this. Yeah, 0 minus, 0 minus, the same one is not allowed here. And other than that, other than you remove this 6 and there should be 15. I didn't count, but I know that because we have calculated in the previous slide. And then what you have here is then L value. The largest L value is, because ML value is running from 2 to -2, the L value here is what? 2. Largest L value equal 2. And largest M value equals what? 1, because it runs from -1 to 1 to 0. Okay, so your L value, the biggest L value is 2, which is D, and L value equals 1, which is P, and L value equals 0, which is S. Okay, so D, P, S terms here, and then S values, largest value is 1, smallest value is 0. So you could do this, and then what happens here is that these 5 terms are all correspond to S equals 0 value. So 2S plus 1, 2 times 0 plus 1 is 1. So your multiplicity for this term, and also this has only L equal 2 value has only this set. So 1D, and then what you have is that S equals 0 or L equals 2, 2 minus 0 is 2. So this is the symbol for this 5 microstate. And then for P, what you get is L equals 1. Okay, the capital L equals 1. And then capital is 1. And then your spin capital is 1, your spin quantum number S equals 1. S equals 1. Because 1, 0, 1 are included, so this is green thing. MS is 1, 0, minus 1. S equals 1. So S equals 1 is 2S plus 1 is 3. So all these P terms are triplets. 3 in the superscript, and then J values are L equals 1, S equals 1, then what you have is 1 plus 1 is 2, L plus S, and minus 1 is 1, up to L minus S, 1 minus 1 equals 0. So 0, 1, 2, 3 terms, and those are corresponding to these 3 terms. And also what you are left is 0 and 0. ML 0, L equal 0, S equal 0 is 1S0. Okay, so this term. So there are 5 terms for MP2 configuration. And then question is, which is the lowest in energy? I would pick this one. Yes. And then that is done by Hund rule. Hund rule says determine not the ground state, even in the ground state the lowest energy. Which is the lowest energy? In the ground state that the lowest energy is the ground state itself. Okay. So this will find you the lowest energy state for the given configuration. So the first thing you check is the maximum multiplicity. Maximum S value is the lowest stable or most stable or lowest energy state. So the first check is the highest multiplicity, and second check is the largest L value. So if it has the same multiplicity, the largest L value, meaning is that D is stable, more stable than D is more stable. P, and then S, like that. And if these two S and L numbers the same, and if that is less than half filled, and minimum J is the lowest energy state. If more than half filled, maximum J is lowest energy state. Okay, Let's do some example. Beryllium excited state is this and has two terms. Well, you can figure out 3s1 and 1s0. So which one is the lowest energy state? Yeah, 3s1, because it has the large s value. And C term, I'm sorry, carbon ground state is 1s2, 2s2, 2p2. This p2, yes, p2, which has we just worked out 1s0, 3p0, 3p1, 3p2, 1d2. In this case, s value equals 0 or 1, so triplet is stable in energy, and then all triplet has the same L value, and then this is less than half filled, so smallest J value is the winner. In this case, the lowest energy state, 3p0 is the lowest energy state. Okay. Okay, so I think this is, we are about done. This is spin-orbit coupling problem. Well, up to now, we assume that spin and orbit does not couple or negligibly coupling. So we ignore this term. But if they couple, what happens? Especially high atomic number atoms, like Z value greater than 40, transition metals, I mean not inner transition metals, of course. Yeah, those things, this is not negligible. So question is that how strong or the value of the spin-orbit coupling interaction. And HSO spin-orbit, yeah, coupling is in this way, expressed in this way. There is a coupling constant and L dot S. Orbital angular momentum operator dot product is the spin-orbit coupling interaction. And then we have J equals L plus S. Then J dot J, well, we just do this calculation. And then L plus S dot L plus S. And then we expand it, L dot L plus L dot S plus S dot L plus S dot S. Then what do we get here? L square plus S square plus 2 times L dot S square, L dot S, then this is J dot J square operator. So what we have is that L dot S operator, just like this, is 1/2 of J square minus L square minus J S square. You recall that L square operator will yield you LL plus 1 H bar square, S square operator yields you S plus 1 H bar square. Okay, that's the kind of orbital and the angular momentum calculation. Of course, J gives you J plus 1 H bar square. Okay, then numerically we can obtain this in this example. So what happened here is alkali atom. Alkali atom has usually in S2 configuration, so which was in 2s 1/2 state, it kind of excited to L equal 1 P, S equal 1/2, meaning it's the P2 state. Yeah, S2 state. Yeah, it does not. In the selection rule of atomic spectroscopy, you cannot change multiplicity. It doesn't change your multiplicity. So same multiplicity is allowed transition, at least in this case. Yeah, of course L number changes just by 1, it's okay. And J number could not, it doesn't change, that's fine. Or it can increase by 1. So it doesn't change, that's fine. This is allowed transition. So we can compute that what is asking you to do is energy level splitting. Okay, this. But this is energy level splitting. Yeah, this is it. Okay, yeah, that's it. So what we have here is that in this expression, Xi or Xi is spin orbit coupling constant, which is A here. So A times this L dot S, which is 1/2 of that, but 1/2 of this, 1/2 is kind of included in J, spin-orbit coupling constant. So J square minus L square minus S square, and then their operation or expectation value is LL plus 1. In this case, L value is 1, S plus 1. In this case, S equal 1/2. Okay, so this number 1 times 2 minus half and 3/2, 3/4 times 2 is 11/4 minus JJ plus 1. And then J value here are different in a way. 2, 3, yeah, this allowed and also that is allowed. So you would have in this transition you have a single line used to be S to P transition, but you would have 2 lines here because both are allowed transition. So it's kind of fine structure in your atomic spectrum. Okay, so J value could be 3/halves and 1/2. So the difference is that JJ plus 1, also JJ plus 1, is that this part is the same in both cases. So this is like 15. So anyhow, this is 3. So this is just 3. So 3A. So this distance is kind of in energy wise, this is 3A. So you divide by this energy difference by 3, you obtain the coupling constant or spin-orbit coupling constant. Well, this is the end of lecture for atomic structure. Okay? Well, actually, that structure means that electron configuration of the atom. So thank you for your patience and keep studying hard.